In this video, we're going to talk about rational functions and asymptotes, and we'll figure out how to find the asymptotes of a rational function. So, a rational function, first of all, is defined by, like this. We have f of x is equal to a of x over b of x, where a of x and b of x are polynomials. Okay, so that makes a rational function, and we should be familiar with some basic rational functions like f of x equals 1 over x. And so this is our simplest rational function, and we've got to have an x in the denominator, so technically this m degree has to be greater than or equal to 1. Alright, so now we want to see how to graph this, and so let's take a look at an example. So when we're graphing these functions, these rational functions, we got to find out the points that make asymptotes or holes in the graph. And we're going to keep in mind that the domain restrictions will give us vertical asymptotes or holes in the graph. And if we look at the end behavior, then we'll get the horizontal asymptotes. So keep that in mind. And so let's look at a specific function. We have f of x equals 3x squared plus 3x all over x squared minus 2x minus 3. And so let's go through a few steps here. First thing we want to do, and these are the general steps for any rational function that we want to graph. We want to write a function in factored form. So we're going to take this function and we're going to factor the numerator and the denominator. And we notice that 3x is a factor of this numerator. So we can factor that out, and that leaves us with x plus 1. In the denominator, we have, we notice two numbers that add to negative 2 and multiply to negative 3. They are negative 3 and positive 1. So we get x minus 3 times x plus 1. Alright, so we've now factored it. Now that it's factored, we can figure out if there's any discontinuities. Okay, so our domain restrictions here, we got to look at the denominator. We look at this denominator, we know that the denominator cannot be 0, so we ask ourselves, what makes x minus 3 times x plus 1 equal to 0? And that is x equals 3 or x equals negative 1. So those are our domain restrictions. Those are the x values that we cannot have in our domain. Okay, so the removable discontinuities, now these are ones where we can actually cancel the factor out. So we notice that this x plus 1 cancels with this x plus 1. And we can write this as 3x over x minus 3. Alright, and so that negative 1 that was just canceled out there is our removable discontinuity. And that's going to be a hole in the graph. Okay, so even though we've just rewritten the function here, we cannot actually use negative 1. We've got to keep that in mind. Okay, so these two graphs, the graph of 3x over x minus 3 and the graph of our original function, look exactly the same except at one point. And we'll see that here in a bit. That's called a removable discontinuity. Then we have our vertical asymptotes, and that is from any discontinuity that cannot be removed. So at x equals 3, we'll have a vertical asymptote. So with that, let's take a look for some horizontal asymptotes now. And we now know that we have a hole and a vertical asymptote that we just found. So now we want to find the horizontal asymptotes. To do that, we're going to use polynomial division, alright, or also known as longhand division. Okay, so we just found out that this simplifies to 3x over x minus 3. So in this step here, you can use this polynomial division with either of these, with the original equation or this one. You'll get the same result. It's a lot easier to use the simplified version, so let's go ahead and try that. So we have 3x, and we want to divide that by x minus 3. Remember, a fraction means top divided by bottom. just like with regular numbers. 3x divided by x minus 3. And so we're going to write that in this form with longhand division. We need a constant, so let's put a 0 in here. And we ask ourselves this: what do we multiply x by to get 3x? And that is 3. So we distribute here. We have 3 times x and 3 times negative 3. And that's going to give us 3x. And 3 times negative 3 is going to give us negative 9. We subtract. These will cancel, and that was the whole idea. 0 minus negative 9 is going to give us positive 9. And this is our remainder. Okay? So our remainder is 9. So we now can rewrite f of x in a different way. We can rewrite it as 3. That is our quotient. So 3 is our quotient from right here. So that's our quotient. And then we're going to have 3 plus the remainder 9 over x minus 3. So this is the same function in a different form. All right? Now we've written f of x in 3 different ways. Now we got to keep in mind, a little side note, we got to keep in mind that x cannot be equal to negative 1, and we know that x cannot be equal to 3. Those are our domain restrictions, so we'll keep that in mind here. So, but with that in mind, this function here is equivalent everywhere except for that x equals negative 1. So now we got to think about limits. Okay, so what happens for different x values? So first we're going to think about what happens when x goes to infinity. Well, when this x value gets huge, it goes up to positive a million, trillion, billion, it gets huge. We have 9 over a huge number, and that's going to be 0. So this is just going to go to 0 when x gets huge. And so when that goes to 0, well, now we're left with 3 plus 0. And 3 plus 0 is obviously 3. And so the limit is 3. And let's check for negative infinity. Well, when this goes to negative infinity, we have 9 over a giant negative number. 9 over negative a million, negative a billion, negative a trillion. And that's 9 over the huge number is still 0. And we have 3 plus 0 is 3. So when x goes to positive infinity or negative infinity, we get 3. And that's going to give us our horizontal asymptote. Okay? So the horizontal asymptote is y equals 3. Okay? And now we also want to figure out what happens when we get close to this vertical asymptote. We know our vertical asymptote coming from right here is x equals positive 3. Okay? Because that was not removed. Okay? Well, what happens when x goes to positive 3? Well, if we put in a number that's a little bit bigger than positive 3, like 3.01, let's make it even closer. Let's go 0.001. So this is going to be 3.001 minus 3. Well, that's going to be a real small number. So that's going to give us like 3 plus 9 over 0.0001. But it's positive. Okay? And as this number gets smaller and smaller, we have 9 divided by a real small number, which goes to infinity. Okay? So this gets infinitely large. Okay? So this thing right here is going to go to infinity plus 3. Okay? So as we have a number a little bit bigger, now this little plus here means that is a little bit bigger than 3. Again, we said that our asymptote is 3. That's our asymptote. Okay? And so as we take a number a little bit bigger than 3, this goes to infinity. Okay? Then coming back here, as we take a number that's a little bit smaller than 3, let's take a number, let's make x like 2.99999. Okay? And minus 3. Well, this is going to be 3 plus 9 over, and this will be negative 0.001. Okay? And so, when you take 9 divided by 0.001, that's a large number. Okay? It should be 9,000. Negative. Okay? Plus the 3. Well, as we get closer and closer to 1, this is going to be a giant negative number. And so this is going to negative infinity. Okay? So this is headed towards negative infinity. So as we get closer to 3 from the negative side, we're going to negative infinity. Okay? So we'll keep that in mind, and now we're ready to graph. So reviewing what we just found that we have a hole at x equals, what was it? It was negative 1, right? And we have a vertical asymptote at x equals 3. We've just found we have a horizontal asymptote at y equals 2. Sorry, let's change that. It was actually y equals 3. Okay, and we'll use the other limits here in just a moment. All right. So let's go ahead and put in those asymptotes there. We have a vertical asymptote of x equals 3, and that goes right here if we're going by ones. We need our scale. This is our x, this is our y, and let's say this is 10, and this is 10, so we're going by ones. Okay, so it's never going to cross that asymptote. We have a horizontal asymptote at x equals 3. I'm sorry, y equals 3. Happen to be the same. They're obviously not always the same. And now the question is, where is that line? Is the graph going to be up here like this? Or is it going to be down here like this? Or maybe they might even be on the same side. Well, to figure that out, we can do a couple things. One, we can test a point, and that's pretty easy. Let's go back here, the simplified version of this. It was 3x over x minus 3. That is true for everywhere except for when x equals 1, negative 1, okay? So now, if we plug negative 1 in here, because we know we have a hole at negative 1, so if we plug negative 1 in here, we have 3 times negative 1, all over negative 1 minus 3, and so that's going to give us negative 3 over negative 4, which is 3/4. Okay, negative 3/4. Right? No, actually make that positive 3/4. Okay, so when x is negative 3, y is 3/4. So negative 3, and we're going to go up 3/4. Okay, so at that point where it seems like it should be, it's actually going to be a hole. So we're going to have a hole there. We're going to put a little hole there. Okay. Now that gives us a clue right there that we have a curve, that our curve is going to be in this quadrant, and it's going to look something like this. And for now, this is a good enough graph. Let's fix that a bit. Okay. Okay. And then our curve is going to be identical. It's going to be a reflection of this, or actually a rotation up in this quadrant. Let's see if we can get a little better than that. Okay. Now, just to double check that, if we go back and look at our limits, we see here that these limits mean as we're coming to the asymptote from the right, we go up, and then as we get to the asymptote from the left, we go down. Let's see if that's true. So coming from the right, we're going up to infinity. Coming from the left, we're going down to negative infinity. All right, and so that's how we have our graph. Once again, we factored to get the hole and the vertical asymptote. We used synthetic division, we actually polynomial division, longhand division, to get the asymptote here. And we found the limits on the end behavior. So that's the main steps there for getting the graph of a rational function. Try it out.